One of the very famous continuous distribution is the exponential distribution. The term continuous is used here in the context of the random variable x taking real numbers as its values. Unlike our earlier distributions like Bernoulli, binomial, Poisson, where the random variable x used to take values 0, 1, 2, 3, 4, etc., here x can take continuous values as well. That is, it can take the values of a real number. Now, when we talk about exponential distribution, the PDF can be depicted in two ways. One of the ways is fx is lambda e to the power minus x, and another way is fx is equal to 1 by lambda e to the power minus x by lambda. The only difference between these two distributions, or is these two depictions of the distribution, is the way in which we interpret the parameter lambda. Here, the mean of the distribution is given by 1 by lambda and rate is given by lambda. Now, what do you understand by the rate, and what is the difference between mean and rate? Let's take an example. Suppose that a customer arrives at a service center, and for the service center to respond to the customer, it takes, let's say, 15 seconds. So the mean service time of a customer is 15 seconds, and the rate at which the organization services the customer is 4 customers per minute. So whenever we talk about rate, there is something called as per which comes into picture. So something happens per a unit of measurement. So if the mean service time here is 15 seconds, then the rate of service is 4 customers in a minute. On the other hand, another depiction of exponential distribution is this. The only difference, as you can see, is mean and rate and variance, of course. Right? Applications of the exponential distribution. The following are the applications. If we try to be more realistic, then maybe if we are near a water body, let's say the event that we are interested in is how many times a mosquito comes and stings us. Right, so those are event, and it's not that only one mosquito would come and sting us at a time. So we could maybe look at the time interval between successive stings of mosquito. If the time interval is limited, then we are in a position. If the time interval is very less, that means we know that yes, this water body has so many mosquitoes around it, and we need to be vigilant and careful before visiting such a body. However, if the time interval is between successive stings of mosquito is large, then we could say that yes, we are in a relatively safe position as far as the mosquito bites are concerned. Similarly, on a highway, if we go on a highway, we least expect red lights to be there on our path, on our way. So if any highway has a red light, then we are interested in knowing the time between successive events. Here the event is when you are stopping at a red light. So if the time interval between successive red lights is very large, that means the highway is a high speed corridor. That means there is no stopping, there is no stoppage in between. However, in case the time interval is small, that means there are successive stoppages in between. Now, as we did before, there are 4 functions governing the statistical distributions of governing the statistical distributions in R. If we just revisit those functions, one of them is D dash dash dash, then P Q R followed by dash dash dash. These dashes are nothing but the distribution to which it pertains to. Let's take a real life example. Supposing at a metro station, frisking is modeled as exponential distribution with a rate of 8 customers or 8 respondents or 8 people per minute. Right, so repeating it, at a metro station, frisking is done with an exponential distribution with a rate of 8 per minute. Let's say we are interested in finding out the probability of a person being frisked in less than a minute. So we use the function P exponential, because I am interested in probability that the random variable is less than 1. P exponential 1 comma 8. So the chances that a person is frisked in less than a minute is 99.96%. It's evident because the frisking is done at 8 customers per minute. So the chances that a customer spends less than 1 minute is almost sure. Right? Next, what are the chances that a customer is frisked in less than 30 seconds? So we could run the same command. In place of 1 minute here, I want 30 seconds, which is 0.5 times a minute. So therefore it's 98.16. What are the chances that the customer is frisked in less than 15 seconds? So quarter of a minute, 0.25, I get 86.46. So that way I can find out the chances. If you see very carefully, the second parameter of the second argument of all these functions is the parameter of the exponential distribution, which is the rate. It is not the mean, it is the rate. Rate is inverse of the mean. If the mean was 1 by lambda, rate is lambda. If the mean is lambda, then the rate is 1 by lambda. So therefore, the parameter here in R is the rate and it's not the mean. Suppose I wish to simulate the number, frisking time for, let's say, 40 people. So I could simply generate a random sequence of 40 observations for a exponential distribution with parameter 8. So there you go. The numbers appear too huge. So if I, let's say, round them off to, let's say, 2 places. So the first guy takes 0.10 of a minute. The second guy takes 8 seconds, the third guy takes 21 seconds, etc. So these are the service times or the frisking times of the 40 customers. Finally, supposing find the total time taken for frisking these 40 customers. So what I can do is I can conveniently store this in a random number, let's say Rn. If I publish Rn, these will be the frisking times of 40 customers. The total frisking times is simply sum of the variable Rn. So it takes 3.94 minutes to frisk those 40 customers. That's what it means. So that was a exponential distribution for you.